Hello everyone, welcome back. Today we cover class section 5.3, logarithmic functions. Lots of stuff happening in this row. Project 2 is officially due today. Project 3 is officially assigned today. And required forum is officially due today as well. Lots of information on Moodle about all of those things. And let's go ahead and get started on 5.3. So here we are. There's another history snippet. Pause the video here, read through it. And we'll begin together on number 2. Let's have a look at the graphs of the common and natural log functions. Which is f of x equals ln of x and which is log x. So pause the video for a moment, see if you can identify which one is which. And to help you identify which is which, if you haven't gotten there yet, we know, for example, that log of 10 is equal to, well, let's actually do one that's not going to help us. Log of 1, how much is log of 1? It's 0, which means that the point 1 comma 0 is on the graph of f of x equals log x, right? Because if you plug in 1 for x, you get 0 for y. Okay, so if we can just find the one that hits the point 1, 0, then we found log of x. Okay, great, right there. This one hits the point 1 comma 0, so this must be the log x function. And the other one is the natural log function. But there's a problem here. If we look at the other one, it also hits the point 1, 0. Okay, let me erase that because now I'm not so sure. The reason that that happened is that ln of 1 is also 0, which means the point 1 comma 0 is on the graph of both functions. It's on the graph of ln of x as well. Okay, so we need some more information here, something more specific to the log, the common log and the natural log. So how about we look at log of 10, for example. That's a nice one. How much is log of 10? Well, hopefully we know that that's 1, which means that the point 10 comma 1 is on the graph of the log function. So 10, 1. Is 10, 1 on the graph over here? 10, 1 is this point, not on the graph. 10, 1 is this point, is on the graph. So that means that this one is the common log. And before we just jump right to the fact that the other one is the natural log, let's see if we can find a nice point that's on here. So we said that log of 10 was 1. What can you say about ln? ln of some nice number. Or ln of some number is supposed to be nice. Let's see, ln of e, that's one of our nice properties. ln of e is 1, which corresponds to the point e comma 1. And remember, e is around 2.7. So does the point 2.7 comma 1 look like it's on the graph? Let's see, we go to 2.7 comma 1. That looks pretty good. Let's go ahead and pretend we can tell that that's e comma 1. So that makes this one the graph of ln of x. Number 3, let's list some properties common to both graphs above. First, we'll start with the domain and range. Domain of both graphs is exactly the same. Remember, domain is the set of inputs, the set of x's that are allowed. Where does this graph start in terms of the x's? Well, if you go to the far left, you will see there is no picture out there for negative x's. And in fact, this guy comes down and it has an asymptote of the x-axis, but it never hits there. So 0 is also not in the domain. So the domain for both of these is all the x's bigger than but not equal to 0. If you prefer interval notation, 0 to infinity, parentheses around the 0, not including 0. Range. The range for both of these is also the same. Where do these graphs start in terms of the bottom? So let's see, follow this guy down. It looks like it goes forever. Follow it up. Well, it's growing slower and slower, but believe it or not, it grows forever going up to infinity. It doesn't level off. There's no asymptote, no horizontal asymptote on any of these log functions. So the range is actually all real numbers. Or if you prefer, minus infinity to infinity. Or if you want to be really fancy, there is a fancy R symbol that stands for all real numbers. Basically an R with an extra vertical line. Okay, next one, increasing, decreasing intervals. Well, these functions are both doing the same thing the whole time. Are they always increasing or always decreasing? They are always increasing on their domain anyway. How about intervals of concavity? Well, these functions are both either concave up or concave down the whole time. Which way are they bending? They are bending downwards as you go left to right. So that means that they are concave down on all the x's from 0 to infinity, their domain. So actually, maybe we should have said always increasing, or maybe increasing on 0 to infinity. Remember, it's always the x's we're interested in for increase, decrease, and concavity. Always x intervals. Okay, end behavior with limit notation. Okay, so as x goes to the far left, so x goes to minus infinity, coming out this way, well, there's no picture there at all, so there's nothing to talk about. But the end behavior on the other side we can talk about. As x goes to the far right, what happens to the y values? Well, we said they go up, and believe it or not, they go up forever. So the end behavior says that as x goes to infinity, the y's also go to infinity. So limit notation. Limit as x goes to infinity of log x, that's the y value, the function, is, well, it goes up forever, infinity. Same thing is true for ln. And finally, vertical asymptote is exactly the same for both. The vertical asymptote is the y-axis. Can you write the y-axis in equation form? I'll give you a hint. It's some letter equals 0. Which one is it? X. Number 4, orders of magnitude and logarithmic scales. Logarithms are used to compress values that vary over a wide range. We actually saw that if you did the activity a couple of classes ago, trying to compare some enormous numbers to each other. I think one of them was 2 to the 2 to the 2 to the maybe 83rd power. And we took a couple of logs and brought it down to size. So logarithms are used to compress values that vary over a wide range. An order of magnitude is a power of 10. The logarithm of the ratio of two quantities is the number of order of magnitudes they differ by. That's a mouthful. The logarithm of the ratio of two quantities is the number of order of magnitudes they differ by. Probably easier to just see that in practice than to try to explain it without an example. Number 5, for example, the center of the Milky Way is about 26,000 light years from Earth. The Andromeda galaxy is about 2.5 million light years from Earth. How much farther away is it than the center of the Milky Way? Okay, it says give an absolute answer as well as an order of magnitude answer. All right, the absolute answer is fairly useless. How much further is it? Well, we're just going to subtract these two numbers. So what do we get here? 2,474 light years. And they say it's fairly useless because essentially we and the Milky Way are right on top of each other relative to how crazy far the Andromeda galaxy is away from us. So much so that the 26,000 light years, which is an absurd distance, is nothing. It's not even a drop in the bucket compared to the 2.5 million. So how much further is the Andromeda galaxy away than the Milky Way? Well, it's basically the same as how far the Andromeda galaxy is. It's basically about 2.5 million. So better would be to think about how many order of magnitudes these guys differ by. So order of magnitude is power of 10. So this one right here is, let's see, 2.6 times 10 to the 4. That's scientific notation, right? And then this one over here is 2.5 times 10 to the, how many here? 6. So again, order of magnitude is power of 10. So the first number is a power of 4, and the second number is a power of 6. So how many orders of magnitude do they differ by? Well, they differ by 2 orders of magnitude. It's not quite 2, because one of them was 2.6 and the other was 2.5. So we'll say about 2 orders of magnitude. That's comparing 10 to the 4th to 10 to the 6th. 2 orders of magnitude apart. But let's see if we can figure out exactly how many orders of magnitude apart they are. So we'll go back to that crazy sentence from the previous page. The logarithm of the ratio of two quantities is the number of order of magnitudes they differ by. So we're interested in this number. How many order of magnitudes do they differ by? We think it's about 2, but it's not exactly 2. We're going to take the log of the ratio. Log of the ratio. And this is not any old log. This is the common log, base 10. We're thinking about orders of magnitude, which are powers of 10. So we're going to do the log of the ratio, big one to the small one. And if we type this in, we're going to get a number that's really darn close to that 2. And it's going to be the exact number of orders of magnitude that these two things differ by. Do you think that they differ by a little more or a little less than 2 orders of magnitude? Pause the video and then come back when you think you've got that figured out. Okay, so hopefully we've come up with something here. So if the number in the front were the same, then they would differ by exactly 2 orders of magnitude, the 4 to the 6. But this smaller number overall has a bigger coefficient in the front, just by a little bit. So it's not quite 2 orders of magnitude apart. It's going to be a little bit less than 2 orders of magnitude apart. So I'm typing in my log of the ratio, and that crazy sentence promises me that this is going to be the number of order of magnitudes they differ by. We're expecting something almost 2, but a little less than 2. What did we do wrong here? 1, 2, 3, 4, 5. Oh, not enough zeros in the bottom. It should be 26,000, not 2,600. And so if we stick an extra 0 here, I have a sense of what I think the answer was anyway, but you might think about what effect should it have, using properties of logs, to stick another 0 in the denominator. Almost exactly the same number. Something to think about. Okay, so they differ by 1.98 orders of magnitude. That's the exact amount that they differ by. Well, anyway, closer. A little less than 2, that's what we expected. So if you want to find out by how many orders of magnitude, by what power of 10 two numbers differ by, you divide them and you take a log. And that makes sense, actually. It's a crazy sentence, but now maybe we can think about it and understand what does this equation say in terms of exponents? Well, we can put in our invisible 10 and then follow the football pattern. 10 to that equals this. So what does it mean? 10 to the 1.98 and change is equal to 2.5 million divided by 26,000. Okay, I guess that makes sense because we're comparing 2 numbers here. So ratio seems reasonable, and we didn't quite get 10 squared. We got 10 to some number a little less than 2. So I think that sentence is reasonable. The number of order of magnitudes they differ by, well, we should divide them and then just figure out what magical power of 10 works. Taking log finds us that magical power. 6. Some scales make use of the logarithm of a quantity. For example, the pH of a liquid describes the acidity of an object. pH is negative log of H+, where H+ is the concentration of hydrogen ions in moles per liter. So if you've got a strong chemistry background, then a lot of those words will have meaning to you. If not, then they won't. It's not that big a deal. This isn't a class in chemistry, but I'm just trying to give you an example of a place where logs are useful outside of a math class. pH is certainly one such example. Regardless of your chemistry background, we should be able to answer a couple of straightforward questions about pH. Part A, battery acid has H+ of about 0.1 moles per liter. Find the pH of battery acid. Okay, let's see. So we're supposed to do negative log of H+, and H+ is given in this problem as 0.1 moles per liter, whatever that means. So negative log of 0.1. And you could just type that on the calculator, but 0.1 actually is one that you should be able to find without the calculator. So you might pause the video here and see if you can figure out what log of 0.1 is, and then we'll come back. Okay, hopefully you made some headway here. Log of 0.1 is actually -1, and there's a negative in the front, so we just get 1 when all is said and done. If you don't believe me, you should believe the calculator, I guess. Oops. So if you type in negative log of 0.1, we should get 1. There. Okay, and presumably battery acid is pretty acidic. So if something has a high acidity, then maybe the pH scale sends it to the number 1. Reasonable. Okay, how about bleach? Bleach has a pH of 12.5. What is its hydrogen ion concentration? Okay, let's see. So in this case, the pH is 12.5, and that's supposed to equal negative log of H plus. And here we're trying to find H plus. So we're going to use the log property, the log definition, but first that negative needs to get out of the way. And then we're just going to follow our favorite football pattern. 10 raised to the negative 12 equals the stuff in here, we should say. So we'll write that 10 to the negative 12 equals H plus, the hydrogen ion concentration. So that's it, 10 to the minus 12. Okay, and I think bleach is very basic. It's the opposite of acidic, and it has a pH of 12.5. So the scale is running something like 1 for the real acidic things and 12.5 for the real basic things. I don't know that these are necessarily the ends of the scale, but they're pretty extreme, I think, on the scale. And the nice thing is that the pH scale here gives us a way to handle numbers that are really not handleable. I mean, 10 to the minus 12 apparently has a pH of 12.5. What happened to that half? You guys got to stop me when I make mistakes like that. So let's put that 12.5 back. So 12.5, 12.5, 12.5. And okay, maybe we should type that into the calculator just to get a sense of how much that is. 10 raised to the negative 12.5. Okay, about 3 times 10 to the minus 13. Okay, so 3 times 10 to the minus 13, that's the hydrogen ion concentration. That number is so close to 0, it's really hard to think about. And if I wanted to work my way over from the basic side, which is this kind of a number, to the acidic side, well, then these concentrations are going to be like 10 to the minus 5 and 10 to the minus 3 and 10 to the minus 2. But 10 to the minus 2 is also really close to 0. So, you know, it's tough to work with numbers that are so close to 0 like that. So the log has a way of taking all those numbers that are scrunched in together near 0, near each other, and spreading them out from like 1 up to 14-ish. Okay, part C. Note that a 1 order of magnitude increase in H plus translates to a blank in pH. Okay, let's think about this. We're increasing the order of magnitude in H plus. So you've got some H plus already in the bag, and we're going to increase the order of magnitude by 1. All right, let's see if we can write in some, we'll find some space in here. So we're going to take the H plus that we had, and we're going to add 1 order, and we're going to increase it by 1 order of magnitude. Increase it by 1 order of magnitude means multiply it by 10. So we're going to multiply this thing right here by 10, and that's going to give us the new pH. Well, anyway, that's going to give us the new hydrogen ion concentration. So 10 of those, and then we know that the hydrogen, that the pH is negative log of that thing. Okay, so negative log. All right, now look, we've got a property about how to handle log of a product. We can split that up into 2 different logs. So it becomes log of H plus log of 10. And don't forget brackets around, whoops, that negative applies to everything. So brackets around the whole thing. And then we'll distribute that negative sign. So we get negative log of H plus minus log of 10. Okay, so far so good, just kind of manipulating the log. I think the hardest part of this is to recognize that a 1 order of magnitude increase means multiply the thing by 10 to the 1. Okay, but look, this negative log of H plus, that's the original pH, right? That's the definition of pH of something with a hydrogen ion concentration of H plus. So then the whole thing is just the original minus, and then how much is log of 10? That's one of the few logs that we should just know by heart. It's 1. So the effect is you take your original pH and just subtract 1. Every order of magnitude increase in H plus translates to a decrease by 1. Or decrease of 1 in the pH. Number 7, another example of logs outside of a math class. Intensity of a sound is measured in watts per square meter. Intensity is a poor way to measure sound since intensity can be very small. Humans can hear sounds as faint as 10 to the minus 16 watts per square centimeter. And because intensity doesn't reflect how we perceive loudness, much better is to measure noise level in decibels. Number of decibels is equal to 10 log of I over I sub 0. This is a definition for how we calculate number of decibels. Just like above, we saw the definition for how we calculate pH, where I is the intensity of the sound, and I sub 0 is the intensity of some reference sound. I sub 0 is just a constant. It's the number, and it's around 10 to the minus 16 watts per square centimeter. It's always that number. The decibel scale gives us numbers that are much more manageable. The sound of a jet aircraft at 50 meters is 140 decibels. A chainsaw is about 110 decibels. So let's see if we can actually do some calculation with this new decibel scale. Next page. If a sound triples in intensity, by how much does its decibel rating go up? Okay, so let's go ahead and put the original formula. Remember, the number of decibels is equal to 10 times the log of I divided by, and I'm just going to write 10 to the minus 16 here. It's just that number. So that's the original quantity. And now we're gonna make the sound more intense. We're going to triple the intensity. That means tripling which letter up here? Is it B? Is it the number of decibels, or is it I? And it's I. I is the intensity. So the new number of decibels is equal to 10 log of 3 times I. It's not just I anymore, but it's triple what it used to be, 3I. Okay, so far so good. Can we do any log properties to this thing right here to try to turn it into something that looks like the original? I'd really like to be able to see this in my formula, log of I over 10 to the minus 16. I really like that part. What I don't like is that part, the 3. 3 is no good. I need to get that 3 out of there. So what operation is sitting between the 3 and the I? It's a times. Do we have a property where we can split up multiplication inside of a log? Yes, we do. I'm just going to make one little erasing here. Let's erase this fraction line, and I'm going to put that 3 just in the front here. I'm not changing anything, but I'm just rewriting the stress. So it's 3, then I'm going to put this dot here, just so we can really think of that 3 as being in the front, being multiplied by that whole fraction. It's equivalent to what it used to be. But now it should be hopefully clear that we take the log and we split it up into the sum of 2 logs, log of 3 plus log of I over 10 to the minus 16. Now I am missing something here. It's real easy to miss, but there was a 10 in the front. The 10 is still in the front of the whole thing. Okay, continuing on, we're going to distribute that 10. So we go 10 log of 3 and log of 3. And then what here? Plus 10 log of I over 10 to the minus 16. Okay, good news. This expression right here, 10 log I over 10 to the minus 16, is the original, and it is exactly what this is here. So then the number of decibels of the triple sound is exactly the same as it used to be, plus that 10 log 3 that's in the front. So this is just 10 log of 3 plus the original number of decimals. So by how much does the decimal rating go up? It goes up by 10 log 3. We can type that in just to get a decimal approximation here. 10 log 3, about 4.77. So if the sound triples in intensity, the decibel rating doesn't triple, doesn't even double, just goes up by about 4.77. Okay, the activity is below. There's a video about it. You can check out the PDF, but really take your time working through this activity first. There's the answer key that you already have access to in this document. This is a tough activity, so give it a good effort and then see if you can take a look at some of those other resources. Learning objectives are in the usual place following the activity's answers.